Evolution and transformation of refrigeration. Refrigeration is a process of moving heat from one location to another, and this has had a large impact on industry, lifestyle, agriculture and settlement patterns. The idea of preserving food dates back to the ancient Roman and Chinese empires. However, refrigeration technology has rapidly evolved in the last century, from ice harvesting to temperature-controlled rail cars. The seasonal harvesting of snow and ice has been an ancient practice estimated to have begun earlier than 1000 BC. It became a mass-market commodity by the early 1830s, with the price of ice dropping from 6 cents per pound to a half of a cent per pound, leading to artificial refrigeration. It began when Scottish professor William Cullen designed a small refrigerating machine in 1755 using a pump to create a partial vacuum over a container of diethyl ether, which then boiled, absorbing heat from the surrounding air to create ice. In 1758, Benjamin Franklin and John Hadley, professor of chemistry, collaborated on a project investigating the principle of evaporation as a means to rapidly cool an object. Their project confirmed that the evaporation of highly volatile liquids drives down the temperature of an object past the freezing point of water. Then in 1820, the English scientist Michael Faraday liquefied ammonia and other gases by using high pressures and low temperatures, and in 1834, an American expatriate to Great Britain, Jacob Perkins, built the first working vapor compression refrigeration system in the world. It was a closed cycle that could operate continuously. His prototype system worked, although it did not succeed commercially. The first practical vapor compression refrigeration system was built by James Harrison, a British journalist who had immigrated to Australia. His 1856 patent was for a vapor compression system using ether, alcohol or ammonia. He built a mechanical ice-making machine in 1851 on the banks of the Barwon River at Rocky Point in Geelong, Victoria. His first commercial ice-making machine followed in 1854, followed by the first gas absorption refrigeration system using gaseous ammonia dissolved in water, referred to as aquammonia. This aquammonia was developed by Ferdinand Carr of France in 1859. His new process made using gases such as ammonia, sulfur dioxide and methyl chloride as refrigerants possible, and they were widely used for that purpose until the late 1920s. The new refrigerating technology first met with widespread industrial use as a means to freeze meat supplies for transport by sea from the British Dominions and other countries to the British Isles. The first to achieve this breakthrough was an entrepreneur who had immigrated to New Zealand. William Saltow Davidson thought that Britain's rising population and meat demand could mitigate the slump in world wool markets that were heavily affecting New Zealand. After extensive research, he commissioned the Dunedin to be refitted with a compression refrigeration unit for meat shipment in 1881. On February 15, 1882, the Dunedin sailed for London with what was to be the first commercially successful refrigerated shipping voyage, and the foundation of the refrigerated meat industry. By the 1890s, refrigeration played a vital role in the distribution of food. The meat packing industry relied heavily on natural ice in the 1880s and continued to rely on manufactured ice as those technologies became available by 1900. By the middle of the 20th century, refrigeration units were designed for installation on trucks or lorries having a maximum payload of around 24,000 kilograms gross weight. Although commercial refrigeration quickly progressed, it had limitations that prevented it from moving into the household. First, most refrigerators were far too large. Some of the commercial units being used in 1910 weighed between 5 and 200 tons. Second, commercial refrigerators were expensive to produce, purchase, and maintain. Lastly, these refrigerators were unsafe. It was not uncommon for commercial refrigerators to catch fire, explode, or leak toxic gases. Refrigeration did not become a household technology until these three challenges were overcome. So in 1930, Frigidaire, GE's main competitor, invented a freon-based synthetic chlorofluorocarbon, CFC, refrigerant, a chemical that led to the development of smaller, lighter, and cheaper refrigerators for home use without danger. These CFC refrigerants answered that need. In the 1970s, though, the compounds were found to be reacting with atmospheric ozone, an important protection against solar ultraviolet radiation, and their use as a refrigerant worldwide was curtailed in the Montreal Protocol of 1987. The introduction of refrigeration and evolution of additional technologies drastically changed agriculture's role in developed countries in the last century. It reduced humidity levels, avoided spoiling due to bacterial growth, and assisted in preservation. A trip to the market before refrigeration would have been different from a trip today. In the late 20th century and into the very early 21st century, other than staple foods, diet was dependent heavily on the seasons and what could be grown relatively close. These are no longer restrictions or limitations. Probably the most widely used current applications of refrigeration are for air conditioning of private homes and public buildings, and refrigerating foodstuffs in homes, restaurants and large storage warehouses. The use of refrigerators in kitchens for storing fruits and vegetables has allowed adding fresh salads to the modern diet year-round, and storing fish and meats safely for long periods. In commerce and manufacturing, there are many uses for refrigeration to liquefy gases such as oxygen, nitrogen, propane and methane. For compressed air purification, it is used to condense water vapor from compressed air to reduce its moisture content. In oil refineries, chemical plants, and petrochemical plants, refrigeration is used to maintain certain processes at their needed low temperatures, like in alkylation of butanes and butane to produce a high-octane gasoline component. Metalworkers use refrigeration to temper steel and cutlery. In transportation of temperature-sensitive foodstuffs and other materials by trucks, trains, airplanes and seagoing vessels, refrigeration is a necessity. All methods of refrigeration can be classified as non-cyclic, cyclic, thermoelectric and magnetic. A refrigeration cycle describes the changes that take place in the refrigerant as it alternately absorbs and rejects heat while circulating through a refrigerator. It is also applied to heating, ventilation, and air conditioning work. When describing the process of refrigerant flow through an vac and R unit, whether it is a packaged or split system. Vapor absorption cycle. In the early years of the 20th century, the vapor absorption cycle using water-ammonia systems was popular and widely used. After the development of the vapor compression cycle, the vapor absorption cycle lost much of its importance because of its low coefficient of performance, about 1/5 of that of the vapor compression cycle. Today, the vapor absorption cycle is used mainly where fuel for heating is available but electricity is not, such as in recreational vehicles that carry LP gas. It is also used in industrial environments where plentiful waste heat overcomes its inefficiency. The absorption cycle is similar to the compression cycle, except for the method of raising the pressure of the refrigerant vapor. In the absorption system, the compressor is replaced by an absorber which dissolves the refrigerant in a suitable liquid. A liquid pump which raises the pressure and a generator which, on heat addition, drives off the refrigerant vapor from the high-pressure liquid are also parts of this system. Some work is needed by the liquid pump but, for a given quantity of refrigerant, it is much smaller than the amount needed by the compressor in the vapor compression cycle. In an absorption refrigerator, a suitable combination of refrigerant and absorbent is used. The most common combinations are ammonia, refrigerant, with water, absorbent, and water, refrigerant, with lithium bromide, absorbent. When the working fluid is a gas that is compressed and expanded but doesn't change phase, the refrigeration cycle is called a gas cycle. Air is most often this working fluid. As there is no condensation and evaporation intended in a gas cycle, components corresponding to the condenser and evaporator in a vapor compression cycle are the hot and cold gas-to-gas heat exchangers in gas cycles. Gas cycle. The gas cycle is less efficient than the vapor compression cycle because the gas cycle works on the reverse Brayton cycle instead of the reverse Rankine cycle. As such, the working fluid does not receive and reject heat at constant temperature. In the gas cycle, the refrigeration effect is equal to the product of the specific heat of the gas and the rise in temperature of the gas in the low temperature side. Therefore, for the same cooling load, a gas refrigeration cycle needs a large mass flow rate and is bulky. Because of their lower efficiency and larger bulk, air cycle coolers are not often used nowadays in terrestrial cooling devices. However, the air cycle machine is very common non-gas turbine-powered jet aircrafts as cooling and ventilation units. This is because compressed air is readily available from the engine's compressor sections. Such units also serve the purpose of pressurizing the aircraft. Thermoelectric refrigeration. Thermoelectric cooling uses the Peltier effect to create a heat flux between the junctions of two different types of materials. This effect is commonly used in camping and portable coolers, and for cooling electronic components and small instruments. Magnetic refrigeration. Magnetic refrigeration, or adiabatic demagnetization, is a cooling technology based on the magnetocaloric effect, an intrinsic property of magnetic solids. The refrigerant is often a paramagnetic salt, such as cerium magnesium nitrate. The active magnetic dipoles in this case are those of the electron shells of the paramagnetic atoms. A strong magnetic field is applied to the refrigerant, forcing its various magnetic dipoles to align, and putting these degrees of freedom of the refrigerant into a state of lowered entropy. A heat sink then absorbs the heat released by the refrigerant due to its loss of entropy. Thermal contact with the heat sink is then broken so that the system is insulated, and the magnetic field is switched off. This increases the heat capacity of the refrigerant, thus decreasing its temperature below the temperature of the heat sink. Because few materials exhibit the needed properties at room temperature, applications have so far been limited to cryogenics and research. Other methods of refrigeration include the air cycle machine used in aircraft, the vortex tube used for spot cooling, when compressed air is available, thermoacoustic refrigeration using sound waves in a pressurized gas to drive heat transfer and heat exchange, steam jet cooling, popular in the early 1930s, for air conditioning large buildings, thermoelastic cooling using a smart metal alloy stretching and relaxing. Many Stirling cycle heat engines can be run backwards to act as a refrigerator, and therefore these engines have a niche use in cryogenics. In addition, there are other types of cryocoolers such as Gifford-McMahon coolers, Joule-Thomson coolers, pulse tube refrigerators and, for temperatures between 2 mK and 500 mK, dilution refrigerators. Fridge gate method. The fridge gate method is a theoretical application of using a single logic gate to drive a refrigerator in the most energy-efficient way possible, without violating the laws of thermodynamics. It operates on the fact that there are two energy states in which a particle can exist, the ground state and the excited state. The excited state carries a little more energy than the ground state, small enough so that the transition occurs with high probability. There are three components or particle types associated with the fridge gate. The first is on the interior of the fridge, the second on the outside, and the third is connected to a power supply which heats up so often that it can reach the excited state and replenish the source. In the cooling step on the inside of the fridge, the ground state particle absorbs energy from ambient particles, cooling them, and itself jumping to the excited state. In the second step, on the outside of the fridge where the particles are also at an excited state, the particle falls to the ground state, releasing energy and heating the outside particles. In the third and final step, The power supply moves a particle at the excited state, and when it falls to the ground state it induces an energy-neutral swap where the interior excited particle is replaced by a new ground particle, restarting the cycle. A refrigeration system's coefficient of performance is very important in determining a system's overall efficiency. It is defined as refrigeration capacity in kW divided by the energy input in kW. While COP is a very simple measure of performance, it is typically not used for industrial refrigeration. Owners and manufacturers of these systems typically use performance factor. A system's PF is defined as a system's energy input in horsepower divided by its refrigeration capacity in DR. Both COP and PF can be applied to either the entire system or to system components. For example, an individual compressor can be rated by comparing the energy needed to run the compressor versus the expected refrigeration capacity based on inlet volume flow rate. It is important to note that both COP and PF for a refrigeration system are only defined at specific operating conditions, including temperatures and thermal loads. Moving away from the specified operating conditions can dramatically change a system's performance.